In this lesson, let us start with ASIC design flow. Now I have a total of 14 steps. So these are the 14 major steps in ASIC VLSI design flow that you'll see. So there are a lot of number of smaller steps, intermediate steps, which we will skip for the sake of simplicity. But if you get these overall steps, I think you should get the idea of the different stages in your ASIC design flow. Now in this lesson, we will look at the first 7 steps and we will go through each of them in little more detail in each of the further lessons. Now we will just have an overview of these steps, and I will also give you a hint of where are the job opportunities in these sections. So the first step is design specifications, and any design, anything for the matter. So you will sit down with the customer and write a detailed design document. And so this will be your guiding document for the rest of the design flow. So anytime you have some doubts based on your design, based on the product, you will go back to your design specs and you will check what was agreed and how your product should be. So a lot of details. It could run into hundreds of thousands of pages. You document everything that the customer requires and whatever you have to offer. So it's an agreement between both the design team and the customer, the person who requires, the team that requires this product. Once you have an agreed spec, then you do something called architecturing, where you divide your bigger problem into smaller chunks, smaller blocks, like divide and conquer types. In your design team, you might have various sections of specialized people specializing in each of the design flow. So you would divide the problem into smaller blocks and distribute it to your team so that they can handle individual blocks in a very effective manner. So that is called architecturing. So you divide, you plan your product and you kind of try and do a bottom-up approach to get to the solution. You also see what modules are already available in your design team and what has to be designed. So we don't design everything from scratch. We always try to reuse the modules that are already designed. So in architecturing, you also plan for what is to be designed and what is to be reused. And some things you just customize. You might have some internal IPs. IP stands for intellectual property. And so intellectual property is somebody has designed it and they own the rights for that particular design. So that is an intellectual property. So you might have some internal intellectual properties, or you might have bought IPs from other companies. Some would be customizable, some won't be customizable. So based on all that, you take a decision of what is to be designed, which processor to put, etc. Now the next step is RTL coding. So if there is something to be designed, so if you don't have all the components that are required and you want to design something fresh, then you will go for this RTL coding. Now this is going to be the most important part of this course. So we will use some languages like Verilog, VHDL, or C or C++, Python. No, these days we can use a lot of languages. No, so even MATLAB can be used for hardware design. Now in this course we will focus on Verilog, but there will be some future courses which would introduce VHDL and other languages. Now RTL stands for Register Transfer Level. Now every design is looked at as, say, flip-flop, combi, and flip-flop. So you have a combination logic between flip-flop. So that is how we look at design. That's the reason behind the term RTL. So you look at designs from flip-flop to flip-flop through a combination logic. So it's always register, transfer. So one register to the other register, we transfer data path, right? Okay, so we will see in detail how to use Verilog to get the hardware that is required. So if you have a good understanding of digital and how to use Verilog to design circuits and how circuits work, you're comfortable translating hardware into code and code into hardware, then you can have a good chance of becoming a design engineer, a designer, right? So using RTL code to implement hardware. Now the language itself is very easy to learn, Verilog, but what takes time is this part, translating your hardware into code. Now you think of a certain hardware, how to get this exact hardware using a certain code. So what code should I write to get this hardware? Or if I write this code, what will be my hardware? So this relationship is what is important, and that takes time to learn. Now we're going to cover this in very great detail in this course. Jobs are plenty in RTL coding. Industries are looking for people with good understanding about hardware and code relationship. Right. The next step is verification. So you've designed something, so you have a certain hardware, and how do you know it performs the intended function? Now another person, so other than the designer, has to verify your hardware. So that person is the verification engineer. So he or she verifies this hardware and checks if this meets the intended specifications that was initially documented. Now if the designer looks at his own design, he may not catch the bugs. So that is why you have a separate team called the verification team. They look at this design without any bias and check all the corners, check all the possible mistakes the design could have. There are plenty of jobs for verification engineers, so freshers. So this is a very good job for freshers because plenty of them are required, and companies usually would require a lot of freshers to work in this area. So it's an interesting job because you will have a close look at the design itself, test benches and models and equivalence checks and assertion methods and so on, so to check the design. If we don't catch bugs here, it's going to be very costly. So this verification step is an important step in the design flow. The next step is synthesis. So this is where the magic happens, that your code gets translated into hardware or hardware blocks. So if you're using semi-custom design, then we will use the standard cell library and pick up a cell or combination of cells from your standard cell library and map them. Your Verilog code gets mapped into one or few of these cells, and they're interconnected with each other. So this is the translation of code into hardware. So a good coding style here, if you followed correct coding style, then synthesis step will be smooth. Otherwise we might have to reiterate and do the design once more to get the correct hardware, the intended hardware. Normally there is no specific position for synthesis, so it's either done by the designer or by the DFT team or by the timing analysis team. The next step is the DFT step. It's not discrete Fourier transform. It is design for testability. So, see for example, if we have a 3-input AND gate, right? And how many possible inputs do we need to give to exhaustively test this chip? So since we have 3 inputs, we need 2 power 3 inputs to exhaustively test this chip. So these days we have chips with an excess of say 1000 inputs or 4000 inputs. No? So how do we check this chip? So after the chip comes out, how do we test it? So we would need about 2 power 1000 inputs to test this chip. So even if you have a clock of 1 gigahertz, it will run into several years. So obviously you cannot test a chip by giving exhaustive inputs. So that is where this step comes in very handy. So what you do is you insert a lot of additional hardware so that when the chip comes out, you can test the chip efficiently. So you won't give exhaustive inputs, but instead you will have a lot of resources inside to help you use less number of cycles. So you're not going to use this number of cycles. You will use far less number of cycles to try and test your chip efficiently. So DFT needs a very specialized expertise, and unfortunately it is not taught in universities. Only a few in the world happen to teach them. The next step is timing analysis. So timing analysis is where you fix the clock frequency of a circuit. So you have done the design and you've synthesized it, you've inserted test logic into it, and now you check what could be the clock frequency of the circuit. You have a certain expectation in your design step, so you check if your expectations are met. Suppose you want your clock to be say 100 megahertz, so you check if your design could meet that. So you calculate and see if your design could meet 100 megahertz, or if not, then what can you do? Which are the critical paths and what are your bottleneck paths and what can you do about it? So that estimate is what is done on timing analysis. Now again, like synthesis, timing analysis is not done by a separate team. The team that usually does the synthesis also does the timing analysis, or it's commonly merged with DFT.